Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at first order logic. So we've previously looked at propositional logic, including all those symbols, implication, and or etc. But in propositional logic, we wouldn't be able to distinguish between a statement like all students play soccer versus some students play soccer. So in first order logic, we introduce these two quantifiers. The existential quantifier, read it as there exists, and the universal quantifier, read this as for all. Now these two have higher precedence than the propositional symbols, so you consider them first. So when we are engaging in first order logic, it's important that we know the domain of discourse. Now we normally write things like this. Px means x has property P. In this case, in this example, Px is going to be the property that a student has blue eyes. So if I write the statement for all x Px, that means that the property P applies to all of x. It means that every student has blue eyes. Now, whether or not that's true depends on the group of students we're talking about. That's why we need a domain of discourse. So the domain of discourse is just the set that you're talking about. So we could be talking about just our class, the whole school. We could be talking about every student in Canberra. We need to establish the domain of discourse. So if we say that the domain of discourse is our class, this statement here is clearly false because there is at least one student in our class who doesn't have blue eyes. On the other hand, the statement there exists Px means there is at least one x that has this property. In the context of our example, this means that at least one student has blue eyes. So this statement is true because we can find at least one student and we only need one such student that has blue eyes. All right, let's look at a more complex example. So here we're going to define Px as the property that x plus 1 is greater than x. Our domain of discourse is the real numbers. So this statement, there exists an x such that Px, that says that there is at least one number x such that this statement is true. Now, that's obviously true. We can find one such example. An example would be x equals 3. So that is an x with this property. That is a real number with the property because 3 plus 1 is 4 and 4 is clearly greater than 3. It's also true for all x Px. It's true that this property applies to all real numbers. Doesn't matter which the real number, if you add 1 to it, you will increase the number. So this statement here says not for all x Px. That means that we're saying it's not true for all values of x. So all we need to do to prove this is to find one counterexample. Now we can't do that here. Obviously, these two are just the negations of each other. So if this statement is true, its negation must be false. So the way you read this one here, for all x not Px. So that's saying for all values of x, in this case for all real numbers, this property is not true. And again, that is false. Now, I wanted to highlight these two examples because a lot of people think that they are saying exactly the same thing. They're not. This one is just saying the property does not apply to all values of x. So this statement would actually be logically equivalent to the statement that there is at least one x, there is at least one real number, such that the property does not apply. Now that's totally different from this statement here. This says for all x, the property doesn't work. This says the property doesn't work for any x. Basically, this says that the property never works. This says sometimes it doesn't work. So make sure that you thoroughly evaluate the statements that you're trying to work with because it can get a bit confusing. All right, let's look at one more example. So here our domain of discourse is n, the natural numbers. So Px is the property that x is equivalent to 1 mod 5. Qx is the property that x is equivalent to 2 mod 4. So let's look at these two statements here. This one says there exists an x such that Px or Qx. That means that there is at least one number that satisfies either of these properties. Now that's obviously true. We can find a number for which either this is true or this is true. A number like 6 works. It is actually true for both P and Q. So this one says that there exists an x for which Px is true, or there exists an x for which Qx is true. Now this is again obviously true, and we can use our example of 6 again. Any number here would work if it satisfies this one or satisfies this one. And if we go through a few more examples, we'll see that these two are actually logically equivalent statements. Any number that makes this statement true also makes this statement true, and vice versa. Conversely, any x that makes this false would also make this false. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.